Hey there, and welcome to The Explainer. Today, we are diving deep into the chemistry behind something you probably have at home right now, aspirin. So let's get right into it. I mean, think about it. You've probably got a bottle of this stuff in your medicine cabinet. It's that go-to, simple little white pill. But have you ever really thought about how it's made? Because it's not just some powder pressed into a shape. Nope. It's the end result of a really cool chemical transformation. So, before we throw on our virtual lab coats and get into the nitty-gritty, let's just do a quick recap of what this everyday wonder drug actually does. Okay, so aspirin is a real triple threat. It's an analgesic, which is just a fancy way of saying it's a pain reliever. It's also an antipyretic, which means it helps knock down a fever. And on top of that, it's an anti-inflammatory drug, so it reduces swelling. It's pretty much the Swiss Army knife of your medicine cabinet. But here's the thing, aspirin is really just the brand name. The actual chemical that's doing all the heavy lifting, the active ingredient, that's called acetylsalicylic acid, and that is the exact compound we're going to learn how to make today. Now, let's zoom in on a couple of its key properties. Acetylsalicylic acid has this super specific melting point, right between 133 and 135 degrees Celsius. And it doesn't dissolve in water. Now, this isn't just a bunch of random trivia, okay? These two facts are absolutely crucial for both making the drug and testing if you did it right, which we'll get to in a bit. All right, time to head into our virtual lab. You can think of making aspirin kind of like baking a cake, really. You need to follow a very precise chemical recipe to get it right. So, our recipe has 3 key ingredients. First, you've got salicylic acid. That's our base, like the flour in our cake. Fun fact, its natural form originally came from willow tree bark. Then there's acetic anhydride. This is our reactor, the chemical that's going to transform that base. And finally, we've got a little bit of sulfuric acid. This is our catalyst. It's kind of like the yeast in bread. It doesn't actually end up in the final loaf, but man, it makes the whole reaction happen way more efficiently. So, what is this chemical cooking process actually called? It has a name, esterification. This is the heart of the whole operation. It's the exact moment we transform our base ingredient into the drug we know as aspirin. We're basically creating a whole new compound, an ester. Okay, so what's this reaction actually like? Well, we know it's acid catalyzed. That's our sulfuric acid doing its job. We also know it's a complete reaction, which basically means it goes all the way to the finish line without stopping. But the coolest part? For sure, it's that this reaction is exothermic. That means once you mix the ingredients, it starts generating its own heat. No stove required. Okay, so we've got our ingredients, we know what kind of reaction we're dealing with. Now let's actually walk through the cooking process step by step. The whole thing really boils down to 5 main steps. First, you mix your ingredients together. Then, as you stir, that exothermic reaction we just talked about kicks in and the whole thing heats up. After about 10 minutes or so, the reaction's done and it starts to cool down. And then comes the magic part. You add cold water and poof, out of nowhere, solid white aspirin crystals just appear. The final step is an ice bath, which just helps even more of it solidify, so you get a better yield. And here's a super important tip, a real chef's note, if you will. You have to use cold water. Why? Because if you use hot water, it'll hydrolyze the aspirin. In plain English, that means it just breaks the new compound right back down into what you started with. It completely undoes all your hard work. The whole batch, ruined. So once all those awesome little crystals have formed, how do you get them out of the liquid? Well, we use a process called vacuum filtration. The easiest way to picture this is like a super high-tech coffee filter. It just sucks all the liquid away, leaving behind this beautiful collection of solid aspirin crystals, all ready for the final step. So, we've made our aspirin. But wait, this is science, right? We can't just call it a day. We have to test it. Is what we made actually pure aspirin, or is it still contaminated with some of our starting ingredients? This, my friends, is the moment of truth. Chemists basically have 2 go-to methods for this. The first is the melting point test. Remember that super specific melting range we talked about earlier? Well, pure aspirin melts right on the dot, between 133 and 135 degrees. If it melts over a wider range, that's a dead giveaway that you've got impurities. The second method is the ferric chloride test. This is a chemical test that's designed to sniff out any leftover salicylic acid, one of our starting ingredients. So that second one, the ferric chloride test, what does it actually show us? How does it work? It is all about the color change. It's a really dramatic visual. If your sample turns that deep purple color you see on the left, that's bad news. It means there's still some of your starting ingredient hanging around. Your product is impure. But if it turns that clear, yellowish color like the vial on the right, that's it. Success. You've got pure acetyl salicylic acid, a perfect synthesis. And just like that, there you have it. We've gone on this whole journey from a few simple powders through a very precise chemical reaction, purification, and testing, all to create the active ingredient in one of the most famous medicines on the entire planet. So the next time you see a bottle of aspirin, you'll know the incredible chemistry that's packed inside that tiny pill. Which, of course, leaves us with one last question to chew on. What other secrets are hiding in your medicine cabinet? Thanks for joining me.